Our solar system is a vast and wondrous place. Among these distant worlds lies Uranus, a gas giant shrouded in mystery. Unlike the other planets which were known to ancient civilizations, Uranus was a relatively recent discovery. In 1781, British astronomer William Herschel noticed a faint blue-green object moving against the constellations. At first, Herschel thought it might be a comet, but after observing it for several nights, he realized he had discovered a new planet. The discovery of Uranus sent shockwaves through the scientific community. It was the first time in recorded history that a new planet had been added to our solar system. Previously, astronomers had only known about the 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Uranus, however, was far too faint to be seen without a telescope. Its discovery expanded our understanding of the solar system and hinted at the possibility of other yet-to-be-discovered worlds. Herschel's discovery was a major turning point in astronomy. This is the story of Uranus, the 7th planet from the Sun, and one of the most enigmatic objects in our cosmic neighborhood. Uranus, a pale blue giant, stands out among the planets of our solar system. Unlike Earth, which spins like a top on its axis, Uranus is tilted on its side. This extreme tilt of nearly 98 degrees means that its poles are where most planets have their equators. Imagine a planet where each pole experiences 42 Earth years of continuous sunlight, followed by 42 years of darkness. Another striking feature of Uranus is its faint ring system discovered in 1977. Uranus's unusual characteristics make it a fascinating subject for scientific study. Gazing at Uranus through a telescope, one is immediately struck by its serene blue-green hue. The secret to Uranus's captivating color lies in its atmosphere. Specifically, it's the presence of methane, a gas that absorbs red light and reflects blue and green wavelengths that gives Uranus its characteristic color. As sunlight penetrates Uranus's atmosphere, the methane molecules absorb the red portion of the light spectrum. Despite these variations, Uranus's blue-green hue remains one of its most defining features. Uranus's atmosphere, while seemingly placid, is a complex and dynamic system. Composed primarily of hydrogen and helium, it also contains trace amounts of methane, water, ammonia, and other hydrocarbons. These trace elements play a significant role in shaping the planet's atmospheric processes and overall appearance. Uranus is classified as an ice giant, a designation it shares with its more distant neighbor, Neptune. This classification stems from their distinct composition, which sets them apart from the gas giants Jupiter and Saturn. While both gas and ice giants are primarily composed of hydrogen and helium, the latter two contain a much higher proportion of heavier elements. These heavier elements are found in the form of ices, not in the traditional sense of frozen water, but rather as compounds like water ice, ammonia ice, and methane ice. The ice giants, Uranus and Neptune, represent a unique class of planets in our solar system. Uranus, a world of ethereal blue, holds within its depths a composition as intriguing as its appearance. Beneath the swirling clouds and layers of atmospheric gases, Uranus harbors a vast icy mantle. This mantle is composed of supersonic water, a bizarre state of matter where water molecules break down under extreme pressure. The movement of charged particles within this supersonic water creates a magnetic field that is both offset and tilted compared to its axis of rotation. Further down beneath the icy mantle resides Uranus's core. The core acts as a gravitational anchor, holding the icy mantle and gaseous atmosphere in place. Unraveling the mysteries of Uranus's interior presents a formidable challenge to scientists. To peer beneath the veil of Uranus's atmosphere, scientists rely on indirect methods. By studying subtle variations in Uranus's gravitational pull on its moons and passing spacecraft, scientists can infer the distribution of mass within the planet. Another technique involves studying Uranus's magnetic field. Uranus's formation, like that of all planets, is a tale etched in the early chaos of our solar system. Billions of years ago, a swirling disk of gas and dust orbited the newborn sun. In the frigid outer regions of the solar system, where Uranus took shape, icy particles played a crucial role in its formation. The most widely accepted theory is that Uranus experienced a cataclysmic collision with a massive object early in its history. This impact would have been powerful enough to tilt the planet on its side, leaving an enduring mark on its evolution. Today, Uranus stands as a testament to the dynamic processes that have shaped our solar system. Uranus, the enigmatic ice giant, reigns over a diverse and intriguing family of moons. 27 known satellites grace its celestial court, each a world unto itself. These moons range in size from diminutive bodies barely a few kilometers across to larger worlds comparable in size to Earth's moon. The discovery of Uranus's moons dates back to the late 18th century, when William Herschel first observed Titania and Oberon. The names of Uranus's moons are derived from the works of William Shakespeare and Alexander Pope. Among Uranus's diverse collection of moons, a few stand out for their remarkable features and intriguing mysteries. Titania, the largest of the Uranian moons, reigns supreme with its ancient cratered surface. Oberon, the outermost of the 5 major moons, presents a darker, more heavily cratered visage. Miranda, the smallest of the 5 major moons, steals the show with its chaotic and jumbled terrain. Ariel, with its bright icy surface, appears as the youngest of the major moons. Ariel is also notable for its system of fault valleys, some of which stretch for hundreds of kilometers across its surface. The moons of Uranus are not static, unchanging worlds. They are dynamic entities, shaped by the relentless forces of gravity and internal heat. Tidal forces, generated by the gravitational tug-of-war between Uranus and its moons, play a significant role in their evolution. These tidal forces can generate heat within the moon's interiors, melting subsurface ices and potentially creating subsurface oceans. This process, known as tidal heating, is thought to be responsible for the geological activity observed on some of the Uranian moons, such as Miranda and Ariel. In addition to tidal heating, some scientists believe that cryovolcanism, a type of volcanism where the erupted material is composed of ices rather than molten rock, may also be active on some of Uranus's moons. This cryovolcanic activity could explain the presence of smooth plains and resurfaced terrains on moons like Ariel. The moons of Uranus, with their diverse features and dynamic processes, offer a tantalizing glimpse into the complex interactions that shape planetary systems. As we continue to explore these distant worlds, we are sure to uncover even more surprises and deepen our understanding of the icy realms that lie beyond the realm of gas giants. Uranus, a pale blue dot in the vast expanse of our solar system, holds onto its secrets tightly. Studying this distant ice giant presents a formidable challenge to astronomers, pushing the limits of our observational capabilities. Its immense distance from Earth, coupled with its intrinsic faintness, makes it a difficult target for even the most powerful telescopes. Ground-based telescopes, while capable of resolving Uranus as a small disk, struggle to discern fine details in its atmosphere or on its moons. The turbulent nature of Earth's atmosphere blurs the light from distant objects, making it challenging to obtain sharp images. This atmospheric distortion, known as seeing, limits the amount of information we can gather from Earth-based observations. Space telescopes, orbiting above Earth's atmosphere, offer a clearer view of Uranus. The Hubble Space Telescope, for instance, has captured stunning images of Uranus's rings and cloud features, providing valuable insights into its atmospheric dynamics. However, even Hubble's sharp vision is limited by the immense distance to Uranus. Furthermore, Uranus's extreme axial tilt and long orbital period pose additional challenges for long-term observations. Tracking seasonal changes and atmospheric phenomena over Uranus's 84-year orbit requires decades of dedicated monitoring, testing the limits of telescope time allocation and scientific patience. In January 1986, humanity caught its first and, so far, only close-up glimpse of Uranus. Voyager 2, a robotic spacecraft launched by NASA in 1977, made its historic flyby of the ice giant, forever changing our understanding of this distant world. The spacecraft's instruments, designed to study the outer solar system, provided an unprecedented wealth of data about Uranus's atmosphere, rings and moons. Voyager 2's cameras captured stunning images of Uranus's featureless blue-green atmosphere, revealing subtle cloud bands and a surprisingly dynamic polar region. The spacecraft's magnetometer detected Uranus's unusual magnetic field, offset from the planet's center and tilted at a sharp angle to its axis of rotation. This discovery hinted at complex processes occurring within Uranus's icy interior. One of the most remarkable discoveries made by Voyager 2 was the detection of 10 previously unknown moons orbiting Uranus. These newfound satellites, most of them small and irregularly shaped, added to the complexity of the Uranian system and provided further clues about its formation and evolution. Voyager 2's encounter with Uranus, while brief, was a watershed moment in our exploration of the outer solar system. It transformed Uranus from a distant point of light into a world of surprising complexity, with its own unique features and mysteries waiting to be unlocked. The tantalizing glimpses provided by Voyager 2 only deepened our fascination with Uranus, fueling the desire for more detailed exploration. Scientists have long recognized the need for a dedicated mission to this enigmatic ice giant, one equipped with modern instruments and capable of long-term observations. Several mission concepts have been proposed over the years, each aiming to address key questions about Uranus's atmosphere, interior, rings and moons. A flagship mission, equipped with an orbiter and potentially even an atmospheric probe, would provide the most comprehensive study of this distant world. Such a mission would allow scientists to study Uranus's atmospheric composition and dynamics in detail, unravel the mysteries of its unusual magnetic field, map the distribution of ices and rock within its interior, and characterize its diverse collection of moons. While a flagship mission to Uranus remains a top priority for planetary scientists, funding constraints and technological challenges present significant hurdles. However, the scientific rewards of unlocking the secrets of this enigmatic ice giant are too great to ignore. As we continue to explore our cosmic neighborhood, Uranus beckons a world of wonder and mystery, awaiting its turn in the spotlight of human exploration. Our journey through the Uranian system has taken us from its initial discovery to a realm of icy wonders and enigmatic phenomena. We've peered into its turbulent atmosphere, marveled at its tilted axis, and explored its diverse moons. Yet, Uranus remains a world shrouded in mystery, its secrets beckoning us to delve deeper. From its blue-green hue to its off-kilter magnetic field, Uranus challenges our understanding. Its rings and moons hint at a history of collisions and interactions. The challenges of studying Uranus fuel our determination to unravel its secrets. Each new observation brings us closer to understanding this enigmatic ice giant. The 21st century has ushered in a new era of exploration, driven by technological advancements and a growing thirst for knowledge. Uranus, once distant, now fascinates us with its enigmatic nature. Observations reveal clues about Uranus's atmosphere, interior and moons. Advanced imaging tracks storms and maps heat distribution. These data refine our models of Uranus's dynamics. The study of Uranus's moons has gained new significance. Evidence of subsurface oceans on Titania and Oberon suggests potential for life. new mission concepts aim to unlock Uranus's secrets. As we stand on the cusp of a new era of space exploration, Uranus beckons, a world of wonder and mystery. The coming decades hold the promise of groundbreaking discoveries as a new generation of scientists and engineers turn their attention to this enigmatic ice giant. Future missions to Uranus will undoubtedly rewrite our understanding of this distant world. Imagine a spacecraft diving into Uranus's atmosphere, sampling its composition and measuring its winds, or a lander touching down on the surface of one of its icy moons, searching for signs of life. These are tantalizing possibilities within our reach. The journey to Uranus is a testament to the enduring human spirit of exploration and our insatiable thirst for knowledge. The future of Uranus exploration is bright, and the discoveries that await us promise to be extraordinary. Kindly like, share and follow us for more expository content.